Earth's magnetic shield is cracking right now, not metaphorically, not as a distant warning for future generations. A coronal mass ejection is traveling toward this planet at 1,293 kilometers per second, and the scientists responsible for tracking it will not know how bad it actually is until approximately 15 minutes before it hits. That number is not a typo. 15 minutes on a weekend. For a storm that could push the outer boundary of Earth's magnetic field inside the orbital altitude of hundreds of operational satellites. That boundary is called the magnetopause, and it is the only thing standing between the surface of this planet and the full energy output of the Sun. The magnetosphere has protected Earth for 4.5 billion years. It is the reason life exists here and not on Mars. It is invisible, it is enormous, it extends tens of thousands of kilometers into space, and it is generated by something happening right now beneath your feet. Liquid iron circulating in Earth's outer core, spinning in patterns that produce a planet-scale magnetic field. When a solar storm hits, it does not hit the atmosphere. It hits that field first. And what happens in the first 15 minutes of contact determines whether this weekend is a footnote in space weather history or something that engineers, grid operators, and satellite teams will be referencing for the next decade. The coronal mass ejection that triggered this alert was observed leaving the Sun's surface in the past 72 hours. CMEs are not unusual. The Sun ejects billions of tons of magnetized plasma into space on a regular basis, particularly during solar maximum, which is approximately where we are right now in the 11-year solar cycle. Most CMEs miss Earth entirely. This one is not missing. The speed is the first problem. Average CME transit velocity is somewhere between 400 and 800 kilometers per second. The shockwave currently heading toward Earth's magnetosphere is moving at 1,293 kilometers per second. That is not a large CME moving fast. That is one of the fastest recorded shockwave velocities in the modern satellite era, and speed directly determines how violently the magnetosphere compresses on impact. Here's what compression actually means. The magnetopause, the outer edge of Earth's magnetic bubble, normally sits about 65,000 kilometers from the surface on the sunward side. During a severe geomagnetic storm, the boundary gets pushed inward. During the most intense recorded storms, it has been pushed inside 36,000 kilometers. Geosynchronous orbit, where GPS satellites, weather satellites, and communications infrastructure live, is at 35,186 kilometers. Do the math on that. A sufficiently powerful CME can push the magnetopause below the altitude of operational satellites, leaving them fully exposed to the direct particle environment of the solar wind with no magnetic shielding whatsoever. That is not a theoretical scenario. It happened during the Halloween storms of 2003. It happened during the Carrington-class event in 1989 that collapsed Quebec's power grid in 90 seconds. The 1989 Quebec blackout is the reference event that North American grid operators have been modeling against for 35 years. 6 million people lost power. Transformers were destroyed. The aurora australis was visible from Mexico. And that event was driven by a CME that, by current measurements, was moving slower than the one tracked this week. But here's the variable that changes everything. The one that NOAA's Space Weather Prediction Center cannot resolve from current data, and the reason why space weather forecasting looks nothing like meteorology, despite having access to real-time satellite data from multiple orbital positions. The magnetic field direction of the CME itself. This is called the BZ component, and it is either the most important number in space weather or the most infuriating gap in our entire monitoring architecture, depending on whether you are a physicist or an engineer trying to protect infrastructure that took decades to build. Earth's magnetic field points northward. When a CME arrives with a southward pointing magnetic field, the two fields are oppositely directed, and something called magnetic reconnection happens. Field lines from the CME and field lines from Earth's magnetosphere break apart and reconnect in configurations that tear open the magnetic shield and allow solar energy to pour directly into the polar regions and cascade down into the upper atmosphere. Maximum southward. BZ equals maximum storm intensity. It is the difference between a G1 minor storm that produces visible auroras at high latitudes and a G5 extreme event that induces ground currents capable of destroying high-voltage transformers. One transformer costs between $3 and $10 million. Lead time for replacement is between 12 and 18 months. The United States has approximately 2,000 large transformers in operation. NOAA cannot measure the BZ component of the CME until it reaches the Dieskova satellite positioned at the L1 Lagrange point, about 1.5 million kilometers from Earth. At 1,293 kilometers per second, the time between Dieskova measurement and Earth impact is 15 to 60 minutes, depending on the exact arrival dynamics. That is the full warning window. That is the entire buffer between detection and consequence. Power grids do not switch off in 15 minutes. Satellite operators cannot move assets to lower risk orbits in 15 minutes. Transformers cannot be isolated and protected in 15 minutes. Aviation authorities cannot reroute the full complement of high-latitude polar flights in 15 minutes. The warning window that exists between knowing how bad the storm is and the storm actually arriving is shorter than most business meetings. This is not a failure of technology. The DSCOVR satellite is doing exactly what it was designed to do. L1 is the only orbital position where the upstream solar wind can be measured before it reaches Earth. The physics of why BZ cannot be predicted further in advance is legitimate and documented and has been known since the first magnetospheric measurements in the 1960s. The constraint is real. What is also real is that the infrastructure exposed to this storm was built largely before space weather was a classified risk category for national security. The North American electrical grid, the GPS constellation, the low Earth orbit satellite networks that now carry global communications, these systems were not engineered with geomagnetic storm resilience as a primary design criterion. Some have been hardened since 1989, most have not. The solar wind is a constant stream of charged particles flowing outward from the sun in all directions at all times. Earth moves through that stream every day. The magnetosphere deflects it constantly, bending the flow around the planet like a river around a stone. During quiet periods, this process is stable and the system reaches equilibrium. During a CME impact, the river becomes a flood. The incoming plasma cloud from a CME is denser, faster, and more energetic than the ambient solar wind by orders of magnitude. When it strikes the magnetopause, the compression is measurable in real time by ground-based magnetometers. Within minutes of initial contact, global magnetic field readings shift. This is recorded, tracked, and is the basis of the real-time storm index that NOAA updates every 3 hours during active events. The storm index is called KP. It runs from 0 to 9. KP5 is the threshold for a geomagnetic storm, the point at which aurora begins appearing at mid-latitudes. KP7 is severe. KP9 is extreme, the top of the scale, a level that has been reached fewer than 20 times in recorded modern history. The current forecast for this weekend's impact, based on CME velocity and estimated mass, is placing probability distributions into the KP7 to 9 range. That forecast was issued without knowledge of the basis component. It is a structural estimate based on the physical parameters that can be measured from current satellite positions. It is also, by the admission of the scientists who produce it, potentially wrong in either direction. If the BISA turns out to be northward on arrival, the storm is dramatically weaker than forecast. If it turns out to be southward, the forecast is the floor, not the ceiling. In May 2024, a sequence of CMEs produced the strongest geomagnetic storm in 20 years. The KP index reached 9 for a sustained period. Auroras were visible from Texas, Florida, and southern Europe. Social media produced millions of photographs. It was widely described as spectacular and benign. What was not widely covered was that GPS accuracy degraded significantly. Multiple satellite operators reported anomalous charging, and at least one operational satellite experienced an unplanned attitude change requiring ground intervention. The 2024 storm caused those effects during a period when the magnetopause remained outside satellite operational altitudes. The current incoming event is faster, and the potential for magnetopause compression into geosynchronous orbit is being actively modeled by every major space agency with assets in that orbital band. This is not a comparable scenario. Airlines operating polar routes are already receiving advisories. Polar routes cross the auroral zone, where the magnetic field funnels solar particles directly into the upper atmosphere. High-energy particle flux at polar altitudes increases radiation exposure for crew and passengers and can disrupt HF radio communications that polar routes depend on as backup when satellite communications degrade. The FAA has procedures for this. The procedures involve rerouting, which adds flight time and fuel cost at scale. The satellites most immediately at risk are not the large GPS or communications platforms. They are the smaller operational spacecraft in low Earth orbit, between 400 and 1,000 kilometers altitude, where increased solar activity heats and expands the upper atmosphere, a phenomenon called atmospheric drag enhancement. As the thermosphere expands, satellites experience more drag, their orbits decay faster, and station-keeping fuel burns at rates not modeled into their operational lifetime calculations. Starlink lost approximately 40 satellites to atmospheric drag during a geomagnetic storm in February 2022. The satellites were newly launched in a transfer orbit and had not yet raised to their operational altitude when the storm hit. The drag increase was not forecast. The satellites re-entered and burned up. That event happened during a KP 5 to 6 storm. The storm forecast for this weekend starts where that one ended. The surface impact of a geomagnetic storm is not radiation. Humans on the ground are not in danger from particle flux during even the most severe events. What the surface experiences is induced current. When the magnetic field changes rapidly, it induces electric currents in long conducting structures. Pipelines, rail lines, undersea cables, and power transmission lines. Those induced currents are called geomagnetically induced currents, and they are the mechanism by which a storm in space destroys equipment on the ground. GICs flow through the neutral ground connections of high-voltage transformers, creating DC offsets in systems designed to carry alternating current. The result is core saturation, overheating, and in severe cases, catastrophic failure of transformers that cannot be rapidly replaced. The Quebec event in 1989 destroyed multiple transformers that took months to replace. The Carrington event of 1859, which predated electrical grids entirely, still induced currents strong enough to shock telegraph operators and set telegraph paper on fire. The Carrington event is space weather's reference catastrophe. A 2013 Lloyd's of London assessment calculated that a Carrington-class event hitting the modern North American grid would cause between $0.6 trillion and $2.6 trillion in economic damage, and could leave 20 to 40 million people without power for periods ranging from 16 days to 2 years, depending on transformer damage. That assessment is 12 years old and was made before the proliferation of low Earth orbit satellite constellations that did not exist in 2013. This weekend's storm is not forecast to be Carrington-class. That statement is made with the explicit caveat that the forecast was issued without knowledge of the Bez component and will remain uncertain until approximately 15 minutes before the magnetopause compression begins. The scientists making the forecast know this. The grid operators receiving the forecast know this. The satellite teams adjusting operational parameters know this. What is different about the current moment compared to every previous major storm in the satellite era is the density of the infrastructure exposed to it. In 1989, there were a few hundred operational satellites in Earth orbit. In 2003, there were a few thousand. As of this year, there are more than 9,000 active satellites, the majority in low Earth orbit, the majority launched in the past 4 years, the majority part of broadband constellations that have never operated through a major geomagnetic storm at full deployment scale. The interaction between a severe geomagnetic storm and a fully deployed low Earth orbit constellation is an event that has no historical precedent and no validated model. The theoretical frameworks exist, the physics is understood. The actual operational behavior of thousands of spacecraft simultaneously encountering elevated particle flux, increased atmospheric drag, and surface charging anomalies has never been observed. This weekend may be the first time it is. Back to the number that matters. 15 minutes. That is the window. That is the gap between knowing and impact. Every power company, every satellite operator, every airline, every pipeline operator with infrastructure that runs through geomagnetically sensitive regions has received the forecast. They are making decisions right now based on probability distributions that will remain uncertain until DSCOVR sends back its first upstream measurement of the actual incoming field. There is no going back from that data point once it arrives. The storm does not wait for a second opinion. The magnetosphere does not pause while engineering teams convene. The compression happens, the field lines reconnect, the currents flow, and the infrastructure that was not hardened absorbs whatever the BZ decides to deliver. 15 minutes from now, the forecasters will know. 15 minutes from that, Earth will. The magnetosphere is held for 4.5 billion years. It is the reason the oceans did not evaporate, the reason the atmosphere was not stripped away, the reason complex chemistry had stable enough conditions to produce biology and eventually organisms that built satellites and power grids and fiber optic cables and cities. It has done its job across timescales that make recorded human history look like a rounding error. This weekend, it will do its job again. The shield will compress, the aurora will expand equatorward, the currents will flow, and somewhere in a control room that most people will never see, engineers will watch field readings shift in real time and make decisions about infrastructure that millions of people depend on without knowing anything is happening at all. The gap between what is occurring and what is visible from the surface is the actual story, not the aurora photographs, not the social media posts, the 15 minutes, the bezel, the cracking shield that has never once in 4.5 billion years failed, and the infrastructure built by the species it protected that is only now beginning to understand what it means to be exposed.